So okay, maybe we'll use slides today. Let me move to here. Um, so we're going to okay, yeah, okay. So the topic we will topic we're going to talk about is like trying to visualize CNN, and I'm borrowing lots of slides from Stanford, and so here, like if you for up to now, I guess maybe I just go directly to um, whatever is CNN. So if you think of like when we have a convolutional network, say for each of the layers here, so for the so what we want to visualize is like for each of the layer, of course we have coefficients, right? We want to see like what the information is correspond to each of the coefficient. So and for the first layer, it probably is a you can kind of observe that directly. You can think of okay, for the first layer you have some filter, and that because just basically the filter is like what you're going to observe, right? Because it's like a match filter. So because like what for the first coefficient here, what I mean is like if you consider the first layer here, if you have an image, it's going to go for a whatever filter here, let's say if just black and white here. So that filter will have a high activation if like it has a good match with the patch here, right? For example, if I filter something like that, then maybe it's a good match at this location here. So essentially you just look at the filter itself, like it kind of give you an idea like what you are expecting like is going to activate this filter. But as you go deeper into layer, apparently you cannot do the same thing. um, you don't know like what exactly in the original image is going to activate the filter. So then like the interesting question is like if we go to the deeper layers, what precisely the the original stimulation in the image that will kind of activate the corresponding kind of coefficient in each of the layer. So of course, I hear like as we said, like we can just show the ways here, but as I said, like it won't be very meaningful if we go deeper into network. So so there are many ways to try to uh, visualize um, this kind of like the filters or like visualize the coefficient in the CNN. So or like that, then I would say like there's three major ways. One way is doing clustering. So attribute, okay, actually this is a, maybe I just finished this one. This is the simplest idea first. So one idea is the following, like if I'm training a CNN to do classification, and I want to know like kind of like not what is stimulating the, I would say like what's stimulating a particular layer or particular coefficient in a layer, but in general, like what is important, like that contributing to a particular class. For example, like this is a dog, but actually what make the classifier believe that this is a dog. So a simple idea, like back in 2013, like is that the authors just think, okay, a very simple idea would be like I would simply have the image kind of mask some of the part of the image. Let's say I have an input image here, and I'm going to classify this as a dog, right? And there will be some score here, like the dog score is like for whatever. Now I just like put a patch, like I just say mask it, random places in the, or like maybe I just mask every places in the image, like this one. I continue to shift this like gray uh, block here, and then like so eventually like for some of the places I will have like a increase of the dog score or the score of the correct class, and some places I may have a decrease. So in this case, if I move this block around, as you can see, like if I am here, then the score for kind of like estimating that this is a dog is actually decrease, the dog score decrease. And this is reasonable. Like if you kind of show out the face of the dog, it's harder to recognize this is a dog. And actually, interestingly, if you see out any other places, you actually will have an increase of the dog score. So because like, there will be less confusion, right? So you will be quite sure, okay, this is a dog. You're referring to this object here. After all, you can have like an image with multiple objects. Then, for example, in particular, if I see out this thing here, most likely I will have like more. Uh, I think this is a ball or something like. Then you'll be sure that like the object that we are carrying with is the dog, is not the ball. So same kind of like example here, like I have kind of classified into the wheel. So therefore, like if I mask out the wheel here, you see like a decrease of the wheel score here. But for many stuff, like for this thing here, if I see this one, I have an increase of the wheel score because I won't get confused. But interesting, I see out here, I will also have a uh, decrease in the wheel score, most likely because we know that this part here mostly like you see this plate here like probably like will only appear in a car, and we know that like car is correlated to wheel, so therefore like if the car score decrease, the wheel score will decrease as well. And also okay, similarly for this guy, this one also, like if I sell here the dog score decrease, and if I see out the face of the man here, the dog score like increase here significantly because we know that okay, definitely we are not interested in the person instead of the dog. So this is a very simple experiment. And and another idea, okay, so as I mentioned, like, this is just a warm up of this visualization. There's several ideas, maybe I'll just say kind of categorize them ahead. So one idea is using clustering. So I'm just cluster things that like have similar representation together, or like if you think of like um I'm for a particular layer of the network as a representation of the input image, then I can just take this like, as a feature and cluster all the input. Like, so then like input that have like similar representation most likely will appear to be similar. So therefore we can use that to visualize images. Um, and another way is I can do backpropagation. So I will elaborate more like what do I mean by that. So it's like essentially it's like I want to have, let's say, just visualize a particular neuron here to see like what is activating that. What I may do is simply starting at this neuron and back propagate back gradient information to the original image and see like what coefficients that correspond to the changes of this particular neuron. So then yet another way, I may do like optimization, kind of similar to this backpropagation idea. So I also try to see like what is going to activate this particular neuron. So therefore, like I was just trying to find an image so that like the activation here will be maximized. And of course, I should add some regularization also to make sure this input here, I mean, appears to be a real image. So we'll go into one by one. We first look at clustering. So for clustering, this is a simple illustration here. We just have basically we look at the, I guess it's, let's see, what does it say? Yeah, it looks like just I take the final classifier and then we say like for all the classes like with similar um, outcome, let's say like for the essentially we look at the last layer, we have the cat score, dog score, and so on, right? And we just cluster them with that final layer. And for this is like for images here are close to one another in that file score. And we can stitch very nicely this way. Um, and this is by tSNE, like the earlier one. Like when we cluster, we need to decide like what distance we're going to do. Right? Of course, like we can just do a simple Euclidean distance. But in terms of visualization, like using tSNE is typically is better. So I guess I will spend. Let's see. I want to get back the. I don't know what's the participant window here. Yeah, okay, see. Okay. Okay, tSNE. tSNE is essentially just a clustering approach. Of course, you can use PCA, but in terms of visualization, tSNE is better. So I will explain why it's better. So before talking about tSNE, let's talk about SNE. SNE is a stand for stochastic neighborhood embedding. So the idea is pretty simple. So you think of like, I have the original samples. So let's say xi, xj here is in the original space. This is like some feature space here. You have some images that like you want to probe into like a particular layer and use that layer as features. For example, like as I mentioned, like this xi here can be the last layer, can be a vector representation of the last layer. So let's say this is the last layer. You have the score here. This is basically the xi. Have a large network, and for the last one, maybe you need to do softmax, or you can even like after softmax use that as a the feature. But anyway, let's say okay, this is the feature here. XI mixed rate for different images. I have like different input. I've had different XI mixed rate here. So I can define let's say the distance between them using a probabilistic model here, like just assume a Gaussian distribution here. So then um, you have something like similar to something Gaussian here, like Gaussian uh, distribution here. So I will have, if like xi and xj are close together, so as you can see here, then there's high probability that they are related to one another. Um, and I can do the same thing in the two-dimensional space. Basically, I have this is like in the high-dimensional space where I want to visualize that in 2D. And Q here will be like the two-dimensional representation. So then the thing is like, I simply, what we want is like, we want to make sure that this PMQ should be similar distribution. And what we can do is like simply using the KL divergence, right? And more, and also like we here, like this is just a minor trick here. Like we can make this like a symmetric distribution. So we define this conditional probability as this, and then like we have Pij is basically the average of the two. So and actually this is actually I'm not even sure this is a necessary. Yeah, okay, it's necessary because this is not exactly symmetric. If you look at that, it looks like symmetric, but it's not exactly because this the the denominator is sum over anything except I here, right? So okay, yeah. So anyway, um, I can define this Pij here just some kind of probability again, uh, formulating in this way, and then I want to make sure that I kind of the Q here will kind of minimize the KL divergence. Um, and to minimize that, okay, it looks complicated, but we can just, as usual, like use steepest descent to do that. So then we can iteratively minimize that. If we do that, then like each time our y here will be updated by something like this. If you look at that, this is like quite reasonable because the KL divergence here is essentially the same as cost entropy and cost entropy, and also the uh, yeah, here, like this step here essentially is the same as softmax, right? This is a essentially a softmax normalization. If you remember, like softmax normalization added with cost entropy, then the partial derivative for that will be just the output. Um, uh, yeah, it's okay. Okay, let's not go into that. But anyway, like, if you do the derivation, will be like this. So okay, this is Lee. Yeah. So the difference of tSNE is just like if you just do SLE here, so if it will be you get you results like it's similar to probably something similar to PCA, but the problem is like with SLE like you will have some kind of crowding problem because um you have like P is in the high dimensional space, right? Typically a 10,000 maybe like a 10,000 dimensions. So then like you can have like lots of labels like in nearby and still it's not too crowded because like they can like fall into like different axes of like the high dimensional space, right? So but on the other hand, like for 2D, like if you want to have every point to go close to one another, then they can become very crowded. Um, so one way to get to mitigate this is like we will just we uh kind of reduce the constraint here, so so that like Q can be not as kind of like concentrated as in the SLE case there. So in the SLE case, remember that like the distribution we use to model the Q or like the one in the 2D um the points to be visualized is using a Gaussian. So if we replace this distribution with something like more heavy tail, so that allow points to be farther away, then you will have data will be less crowded. So that's exactly like what they did in tSNE. So in tSNE, like instead of using a Gaussian distribution to model the visualized data there, we just use a T distribution. So therefore we call it tSNE. So then the T distribution allow you to have a heavier tail. So then like, it will visualize much better. So, and if you try to kind of derive that, you will see that the update rule will instead become something like this. And essentially, like you see that you can think of uh, yeah, you can think of this update rule separated by something like a spring and also some kind of force here. The spring will be like if you have like 2 points to start with, like yi and yj, let's say, um, they are in the original space. If they are far away, let's see, then you are going to push them apart as well, right? Or like if they are close together, then they will pull them together as well in the um in the visualized space there. So and then this will be some kind of force. Like it will be if they are far away, then like this will be big. If they are close together, this will be small. And then like uh you will kind of like modulate with like some kind of force here, like by this thing here, to see like how much force eventually you apply to the points there. Um and uh okay. Okay, I yeah, okay. So anyway, there's some minor trick here. Like okay, I guess I don't get into here. Like just you can speed it up, for example, like using quad tree, or like and also like you can speed it up a little bit, like if you group some of the, because if you think of that, like if your points moving around, like for example, like you have this here, like each of these point like is going to pull you, right? like somehow like can pull you like to the new position here. But if you have like group of pawns here, that's going to pull you more or less along the same direction. So then you can first like group all these pawns and compute a left force here, and have this left force just pull this pawn once instead of like pull this many times. So this can speed up a little bit. And this is like kind of like trick using astrophysics, and as long as it's bounce hard approximation. Um, and this is using tSNE for visualization. And now let's go to the second approach using like backpropagation. So sometimes people also call this deconvolution, or maybe backpropagation is better. So you see the idea is very simple, right? But there's a couple trick here. So essentially you have a point, let's say I want to visualize a particular coefficient here, let's say this coefficient here. Now I just backpop all the way to the original image, right? So just think of, okay, I have this value, backpop all the way. I can of course use the original backpropagation, but the result won't be very nice. This is like the result, kind of you see like this is like backpop to the, I believe is the actual class of this cat here. So basically you go to the final layer. So let's say there's a cat score here, and then I just look at this cat score and then backpop all the way to the beginning and see like what do we get. And it doesn't look good, like something like oh, sorry, okay, this actually look good, but if you just use regular backpop, it doesn't look good. um so there's some trick to do that. Actually, by the way, this original conflap paper, the conflap paper, is appear also in this Fergus paper like back in 2013 that we mentioned that they have this occlusion experiment, right? So it's a pretty nice paper. They have like a couple ideas in the paper. And I'm now doing backpop, like what they have, they say, okay, I can, if I do regular backpop, it doesn't work well, then they modify the backpop a little bit. So instead for the, basically, for the pooling, like we mentioned, remember, like we mentioned last time, like when we do this telescope kind of like uh, have image that, what I want to say, if I we last time we talked about semantic segmentation, uh, using a CNN4 layer, typically you downsample the image, right? So if you do some semantic segmentation that like the output have the same dimension as the input, then you need to upsample somehow like in the later layer, right? So if you have pooling here, that the downsample, you need to have a pooling here, like kind of unpooling here uh, in the later layer as well. So there are many ways to unpooling. For example, one is like doing this kind of like well, how do we call that? I forgot, but uh, s- um, but basically, like if you just activate the points that actually do the pooling operation. For example, if you remember, like if during pooling, I have, let's say I have like four coefficient here, 2, 3, 3, 1, 2, 4, let's say. Then if I do pooling here, like for these four values here, I will be basically just, this one is like actually is the maximum, right? So I'll get 4 here at the output. Now if I do unpooling, maybe I have a 5. Okay, maybe I have some values here. Like of course after many layer it won't be the same. Maybe there's 5 here. When I do unpooling, I will only like give non-zero value to the same place that I get the maximum. So other places will just have 0. So that's what they did here as well. Uh, and also filter, they do the transpose convolution that we mentioned last time. So basically, this tool is very natural, like just what we expected. For the value, it's like different because if you think of backpop, um, yeah, actually, this is a good question to ask. Like, let's say if I have a value minus 1 3, let's say. Now I have a value, then I of course I get like 1 1 0 3, right? Now when I back pop back, I have like some gradient values here. Let's say it's like minus 1 1 to -1, let's say. So what will be this value? Maybe so this is value here, right? This is backpop. So what is the value for, what will be the value for the original backpop for value? So is my question here? It's just like this is a regular backpop for value. So forward, like let's say this guy forward, right? Forward, I get this one here. Now I backpop, like what should be the value of this thing? Have someone answer that? So any more answers? So you guys are working on that, or like is the question clear? Okay, so I have maybe not everyone is around, I guess. So okay, I guess the majority is correct. So know that like when we do back pop, when we do forward here, what back pop is doing is like really it's just the the train rule in calculus, right? So again, like I'm should be, when I do back pop, I should propagate back the this gradient multiplied by the local gradient here, right? And the local gradient, if you think of that here, uh, the gradient should be when this is positive value, then I will be in this region, right? So therefore, the gradient is just, or like the derivative is just equal to 1. But if it's negative here, then I will in this region, then the derivative is just equal to 0. So therefore, like if you think of the local derivative here, it's just really 1, 1, 1, 0, right? So then if multiply with this propagate back, so therefore -1, 1, 0, -1, yeah. So okay, this is for regular back propagation for value. But what you see is like for what they propose by Fergus here is like uh we simply use value to do that. Like, it's not a regular back pop. So what they do is like I will do back pop here as well. So therefore, when I back propagate back, actually I will get like 1, 2, 0, 0 here in this case for how they do the visualization. And they call this like Deconv flat. And that's the results is so quite pleasing. So for example, like if you look at like later layer, like if you look at a particular nuance, I guess it's a layer of they look at like different nuance here, and it looks quite nice. Um, and that's also like later layer. And again, I just like um doing this the conflict. There's other approaches. There's uh, that's one. Okay, this one, of course, I just do backpop, regular backpop. This is like what we have here. As you mentioned, I do regular backpop. Um, let's say, okay, let's look at this example here. So this is very similar to what we have earlier. So we have like, uh, again, for all these different approaches here, only the valued operation here, they make changes like for the backpropagation, and for the conf layer, and also for like pooling, they more or less do the same thing, exactly do the same thing. So for this one here, like I forward is like this, like the previous example, this is negative, so this is 0. Now if I do regular backpop, then I will have only these places that should be kind of set to 0 here, because they actually have the local gradient is equal to 0 if this is like the original backpop. And this is the one that we just mentioned, the conflat, that will simply do the backpop in the opposite direction as well. So that's some other approach. They call it guided backpop, just combine these two together. So in the sense that they only propagate back when when there's when both of them are non-zero basically. So when like you're going forward, like it's non-zero, and also going backward is non-zero. Oh, sorry, both are non-negative, I want to say. So, or like both of them are positive. So if you're going forward, like this 4 places, 0, then we will set to 0. But also like this is a negative, also we will set to 0. So basically just, so this is like a guided backbone. I don't know whether I have, yeah, I have some, it looks like even cleaner. So it is a bit ad hoc, to be honest. Like, so, but it just worked well. So I guess some of the rationale here is like, uh, you just want to, you don't want to show activation of both like positive and negative activation, because like um uh you can have like, for example, like uh if if the if something, uh what I want to say, if I think of a coefficient here, somehow how whatever the image eventually uh, will be kind of like related to this coefficient. So if I change it like in one way, for example, if for some this coefficient, if I activate it kind of like, or like if I increase kind of like the intensity of this pixels here, um, let's say if I have this value increase, then of course I got this activate, right? But I may also have cases that like if I increase the intensity here, the coefficient actually decrease. But in this case, if I just ignore the sign here, if you think of this here, like if we backpropagate like either way, or like we backpropagate like this one, actually essentially this one, we're ignoring the sign here, then like we uh we will capture the activation or like the stimulation when we both like make the coefficient like more, or like the pixels that like make the coefficient like uh um more both stimulating the coefficient or like trying to suppress the coefficient will be included in the visualization. So therefore it will make it a little bit more messy. So therefore you probably want to chop off one way or the other. So therefore like applying this value is good. So anyway, like this is the backpropagation idea. Um and and uh and we can use this to this kind of idea for some real application. For example, like I can use this to find the salient map of some image. So I can like forward image, and then like I can see like what vision of the image is actually activating um, the corresponding pixel. For example, like if I have uh, any just an image here, this is exactly a word called grab cut that like I trying to do a nice segmentation just of this object instead of like everything else. So of course, like this is an earlier work. Like nowadays, you can really do a semantic segmentation. I guess we do pretty good job. But this probably like this may be a bit challenging still. So in this one here, they kind of you just do it forward, right? And then afterward, you classify this thing here. Then you go back and see what pixels actually activate this kind of like get this grasshopper here. I think it's grasshopper, and then you just say do a segmentation only on this pixel, so therefore you get a cleaner segmentation result. And this is the same thing here, also like for snake and so on. Um, so this is just more visualization. Okay, so now look at the third approach here, using optimization. So we mentioned that we can do clustering or like backpropagation. Now for optimization is a very simple idea. So I let's say I want to see like what kind of image will be activating a particular pixel here, or sorry, particular coefficient here. So I can just fix the coefficient. Let's say I fix a representation here. I'm trying to find the image going to maximize this or like get closest to this guy as possible, as much as possible. So more precisely, it would be like this, right? I have a layer here. So let's say I want the representation to be a particular fine seal here, and then find the image such that these two will be as close as possible, measured by some kind of loss. Maybe I can just use square loss here. So typically, you need to some kind of localization. So for example, like I don't know, any kind of localization, because like otherwise you just get something like totally noisy, just white noise there. And so this is some earlier work demonstrating that like you have the original image, and then like you just after you get basically what they did is like uh, you after you input this image here, you go to the you have a representation of this layer here, right? Now you go back and start the optimization again, and just say you start with a randomized input here and try to see like what will give you a best match of this guy here. So then you get like images like this. It's not exactly very pleasing, like this is like kind of earlier work, but it's getting much better now actually, because of GANs. I will talk about GANs later on. So this is also an illustration. Like say, if I trying to reconstruct for, okay, maybe it's a good question to ask without showing that image first. So let's say I have this kind of approach here. So of course I can also like fix in earlier layer, right? So let's say now I have like just A B testing, I don't know, A and B here. So and I want to see let's say I have some image to start with, right? And then I when the image pass through and then I get a representation here. Maybe I call this like phi x, and then they go. I mean this one. Let's see what uh uh phi psi x maybe. Mm, psi x. Let's see. Now maybe I call this A. Maybe I call this B here. So now if I go to this optimization, and I get this X tutor here, the new image. So this basically I go for X tutor is like arc mean the difference between like let's say this phi x is equal to maybe phi zero here, or maybe I can write like this. Maybe I can loss of phi x and phi x pi here. Let's say I may have some regularization x pi, let's say. Now, so this is my case A, right? So I solve for this x tilde here. Maybe I call x tilde A here. And I can do the very similar things, right? I can have like case B here, xb tilde arc mean x pi here. But I want to match this layer instead. Psi x and psi x pi here plus lambda r x pi here. So my question is like, compare A and B, um, which one is more similar to X? So either like X A tilde and XB tilde, which one will be looks more similar to X? So is my question clear? Yeah, my question is something like that. So if I want to reconstruct, so in the sense I'm trying to reconstruct an image. Now I start with an image X that's exactly something similar to, let's see, something like this one here. Yeah, but I guess it's okay. Okay, this page is okay. This slide is okay. So we start with some image X here, and I pass forward. Then I at this layer I have something like, let's say have something like phi x is equal to the output at, I mean, or like the coefficient at this layer. And I at this layer I have psi x is the coefficient at this layer. So I can reconstruct image using constraint to match at this layer, match at this layer. So for more precisely, if I want to match with coefficient at this layer, then I want to try to find the x pi here, that this phi x pi is closest to this phi x, right? So we have a small loss as possible, added with some, say, some regularization, and I can then reconstruct this x tilde a here. And I can also, like, instead of matching, try to matching coefficient at this layer, I can try to match coefficient at this layer. So instead I try to match, like, okay, this looks a lot similar. This is like psi. So trying to match this side to be as close as possible. Now my question is like, which one should look more similar to the original X? Yes. Yeah, yes. Um, uh, yeah, okay, yeah. It's reasonable, right? So if you move all the way here, then of course, when you get farther and farther away, you just lost more and more information. And if you uh, get back to the earlier layer, you try to match that, then you should get more similar to the original image. And you observe this also like here. So if you go down to the later layers, I guess it's go. This is a, I think maybe Alex led or whatever. So it's trying to match different layers here. So if you just match to the next layer, you get very close to the original. But as you go down like to the almost the last layer, you get something very different. Um, and and we yeah, I guess I hear say you can match the entire layer or something, but or you can match just for a particular class. Um, so then uh, in yeah, actually very similar to before, but it's you see like okay FC7. So this one like is I think FCA is uh yeah I think this is also last layer, but of course you can match the last layer. So essentially do the same thing, but I'm trying to match the last layer and we'll be interested to see like what we get here. Um, and so here some result if you just match the classes. So again, I did something that's pretty early, say almost what 7 years ago. Um, so now it's getting much more impressive the result. But as I show you later on, like some other slides also getting is more impressive than this one. So you see, like more or less, you can see that. Like for the class here, for example, the lemon, the cup, you can kind of more or less see the cup here. I guess it's a cup here. I don't know the word that measure. Anyway, maybe some kind of animal. I guess that you guys know. Oh, yeah, I guess it's some kind of dog, right? I guess yeah. You see the hat here. Um, and we can improve that like through the visualization. So the visualization here, I believe, is just trying to do the earlier work. Just use the gradient, kind of like smooth the gradient. So of course, it's not actually doing really well. And so and also another problem like that it doesn't look too good is like if you think of like classes, like if you're in the last layer, for example, if I classify into chair, so I think of okay, this is chair, let's say, then I just backpropagate or like not backpropagate, but just find the image that maximize the chair class. But we have many different kind of chairs and they can look very differently. And so one work that have been done here is that like we can just like think of like um, instead of like uh, trying to like have a chair but that is going to visualize all kind of chairs, but just like focus on one chair, let's say. So how they did that is like, okay, I can consider like um you what I want to say is like you start with like still start with one image, then you when you go so let's say so I guess I has an example, for example, food and supermarket here. So I can have supermarket like represent by like have some food arrangement here, but I also can see as a cashier here. So I want to make sure that I don't have a blending of these two very different images. So then what they can do is say, okay, I start with some image sit here. So actually very similar than to before. Then I optimize not from my random image, but optimize from like a custom representation of this. So something like for example for supermarket, like I have like several different images can be all like kind of similar to supermarket. And then I would just say clustering these kind of images like together so that they have like similar kind of images. For example, like one image correspond to cashier, the other image correspond to like food there. And then I will put all these images together and get an average image, and then I use that average image as seed to do the optimization instead of like just starting from like a random thing to do optimization. Because after all, like when you do optimization, you just do gradient descent, right? So you just so instead of like start with something random, you start with something I see there. So and that give you better results like this one. And then like you can do even like this is a much closer to like recent work now. So it's very similar to before, but like just we improve the pi quite a bit. So we'll talk about that later on, like using GANs. So in instead of like in the earlier work, like we say like something is looks like an image by just like saying that like the, for example, like the image should be relatively smooth and so on. The um the the sum of derivatives should be relatively small and that kind of regularization. Here just add a prior that is p-train. So it's like you train a GANs model and the GANs model will be added as a prior. So it's more like this one here. So the GANs model that we'll explain later on will be something like if you plug in some code here in the input, you'll just get some image here. So then when I want to generate an image, for example, a candle here, I'll just like put in the this part will be just the part that do the classification, right? This part will be the GANs model. Then I just train all the way back part all the way to the code here. So I'm not training to modify the weights, but I'm training to modify the code. So for example, given a candle here, I try to back pop to find the value of this code will be maximizing this candle here. And then once I find this code here, then I will have this image, right? So then I can put in this code and generate this image. And the result looks quite impressive, like this one here. Like so, if you're giving different class, you get say something like kind of very nice, um, very pleasing. And okay, I guess I also mentioned something about deep dream is kind of interesting, like to look at. So this is like some uh, interesting artwork like generated by deep learning. So very simple idea basically. Um, the idea is following. So it's just trying to think of okay, if I train a model here, what I call it dream is like in the sense like you can think of like okay, if you have an image to start with, you just look at that and think of like what does the image look like, and I can't reinforce that. So for example, I look into the cloud here, so maybe the cloud here somewhere somehow it looks like a dog here or a bird here. So I just like trying to modify that to make it more like a dog and so on. So then to as long as we do that, we get something like very interesting like this one. So lots of eyes and lots of dog, actually lots of dog faces. Lots of dog faces because in the model itself, like there's lots of dog samples there. So therefore, if you look at everything looks like a dog or an eyes. And so then like precisely what it did is a simple backpropagation. So you again, you're just trying to do backprop to modify the image instead of modify weight, but you more modify the image, you backpropagate back the gradient that's simply equal to the kind of like the coefficient itself. So so that's simply that. So therefore, like if for that particular layer, if like the coefficient is big already, right? So it's big there. So you make it even bigger in the sense, right? So then like you reinforce that have this exactly this idea of like everything like if it, everywhere if it looks like a dog, you make it more like a dog. And this is deep dream, and this is like some example like based on like different data you train, you can see different things, right? For example, like you have like using image lab, you have like lots of dog like images like coming up. But if you use like some architecture like image, or actually then you everywhere like looks like architecture basically. And also like if you try and like dream at different layers, you have different effect as well. If you dream at earlier layers, you have like more low level features coming up, right? For example, like you have like more textures. Uh, Instead, like if you dream at a later layer, you get more abstract semantic, like for example, dog or like cats and so on, like in your image. And another thing like related to artworks, like is something like mural style. I guess like this have been like adopted like already in applications. I guess probably like if you, I don't know whether like Photoshop have that. I guess maybe may or maybe not. I don't know. So, but this is a um, again a simple idea that if I start with one image as a this image here, I want to like create another image that based on this the context of this image, but based on different styles. So for example, I can extract styles from uh, maybe Picasso, and then I get something like Picasso like image of this one, or I can yeah. I can get something like the Starry Night and something like this one here. Um, so you can see this illustration for that. And the way to do that is like, again, it's actually a simple idea. So you just have two images. One is give you the context, the other is give you the style. So more precisely, you have basically you have a lateral like this, you have a lateral coming in, and one of this is a the output image is just you start with a noise here, like putting in there. So you try to have like this image to match with the styles of the style image and the content with the content image. So for example, in here, like you may take one layer here, make sure that the content of this white hat here will match with this the content of this white here at this layer. And then you try to like say like for this uh also like for these several layers here, we're trying to match the styles. And for match the content is simple. Match the content with simply like the basic Euclidean norms there. Okay, I don't have a slice here actually. Oh, okay, I don't know. Okay, yeah. It's basically just a content will be, it can be just square distance if you want to match content, but matching the style, like we can match say the grand matrix basically. More precise, it's really like the coherence matrix. So you have the data there. You does not match the data directly, but you match the coherence matrix of the data. And interestingly, this capture like more or less the style of the image. So then like you just like match style like as several layers, then you get like nice result like this. Um, one one thing though, like this is like just worked like a couple of years ago, like 2016. But immediately people get lots of attention and interest like on this, and so therefore like lots of like improvement. So first thing like the first major improvement is that like this is great, but the problem is like this is pretty slow because like, you need to go through the uh this is really an optimization problem, right? So it's like really training the lecturer. So you each time you want optimization, you know, training is slow, so it takes several hours to generate this image. So um okay. So what they did immediately, some improvement is that like, okay, instead of like, okay, actually this kind of trick has been done like many times. Is that if you have some procedure is slow, why not just train a feed forward lateral to do that? Because feed forward lateral is fast. It's just a bam, matrix multiplication, value, matrix multiplication, value, and so on and so forth. Super quick. So therefore, like instead of like just that trying to generate, I mean, trying to train this Y hat, we instead like if you compare to the earlier one, we just have a random image coming in and trying to train this Y hat here. So instead like we have the input now to a, we will basically have the content image put into the feed forward lateral as well, and have the feed forward lateral to generate this Y hat here. I'm trying to train this lateral instead. And also the nice thing is like when we do that, like uh, not only is fast, we can adjust for different style, right? We can put in different lobs there. Let's see, for example, like this one here. So uh, we can use a okay. Um, we can, okay, this is a instance normalization. It's basically, like, if you remember, it's very much similar to batch norm. But what they're doing is, like, in batch normalization, you normalize the entire batch. Here, you just normalize one image, so one input. And I mean, if you remember, like in batch norm, like you do a normalization afterward, like you also like have this you can do a inverse operation, like basically rescale your uh, image or rescale your data variance and also like the mean there, right? And shift the mean. Here, like what it does is like, okay, I will have this will be like adjustable. So in the sense like when I train that, I'll train this guy as well to adjust the effect. So then when I modify this guy here, so like I learn like how to modify this gamma S and beta S such that will give me the different effects. So for example, like if I simply adjusting, it's like some kind of lock here, like or like yeah, some kind of button or like sliding bar here. As we change the values for this one here, so we can have like different kind of effects. Like for example, like you can get up to like these styles, can have an interpolation of styles, right? So I can have like a starry night style, or I can have a I don't know what, but this is a what this is so famous, a scream style, and like different styles, and then you can interpolate with one another as well. So it's super neat. Um, and actually, okay, I guess I'm pretty quick. Uh, and maybe couple things that like it's it's kind of not exactly related to visualization, but I guess it's a little bit relevant. Um, is that like, and also it's not just limited to deep learning, but it's like this is a phenomenon for all kind of classifier machine learning model as well. Is that like it's actually if you know the model precisely, it's very easy to fool the model. For example, like if I have this is like of course a school bus, but I can like just modify this image a tiny little bit, just add this like image difference here and create this image is like very much to the classifier belief that is an ostrich. And this is the same for this kind of images as well. Like I have this dog, I can add this tiny distortion and it become like a bird also. Um, so and if you think of that, this is very reasonable. Like that is possible because after all, like all the classifier is just what you are doing is a you can imagine it's like just doing simple clustering, right? So you have like several classes. I say this is a cat, this is a dog, and so on. So this is a bird maybe. And if you know like the model, the classification model, and if you're a cat here somewhere here, I can always just move along this direction, let's say, precisely this direction, and I can get close to the bird, right? And oftentimes like this gap is actually not big, or like you can make slight enough difference because if you know the, of course, if you don't know the model, like if you just make random modification here, then remember like here I draw like this is like only a few dimension, but this thing is really in high dimensional space, right? So cat here, if you the cat image, I say is 100 by 100 pixel here. So I'm in really in 10,000 dimensional space, right? Therefore, like even you think of orthogonal direction, that's like 10,000 like orthogonal directions, right? To pick for. So then um if you don't know the model, it's very hard to get to that right direction. But if you know the model, then it's not difficult at all to get to the right dimension to make tiny changes to make a cat become a dog, or cat become a dog, or cat become a bird, and so on. And this is something that like is almost impossible to avoid, I believe. Um, of course, even though but I'm not on top of this line of research though. Apparently, people are Also, this is an interesting research topic. People look at our salary model and want to see like how you're going to trick a classifier to believe like this is one thing instead of the other thing, and so on and so forth. And this is another illustration that like with very high confidence, 99.6 confidence actually, to believe this random kind of like random noise, like white noise, looks like for example, this looks like a panda, less a panda, this looks like a bubble, and this looks like a jackfruit, and so on. Um, and this is another one, another illustration. This is a baseball, like electric guitar, and so on and so forth. Um, and as I mentioned, this is not really new things like to deep learning, deep neural network, neural network, deep learning. It's actually same for all classifiers. For example, like for the P deep learning era, using for example HOG descriptor with like SVM to classify a model, classify an image. You also can have like almost identical representation. For example, like these two are both look like okay, or basically this I think is this is like dragonfly, I guess. Looks like a dinosaurs. Um and yeah, this is an okay. Just repeating like what I explained earlier. So this is a quick conclusion that I guess I go pretty quickly this time, I guess because maybe I'm using slides like this. Uh so again a kind of like a summary of what we talk about today. So visualization, the three approaches is okay. How about I just check like how many people are still around? So I can do clustering. Um, I can do optimization. What's the second one? Do you guys remember? Yeah, that's fine. It's good to know that you guys are still here. Yes, we can do back propagation. Yeah, it's very similar to optimization, but yeah, it's um and that back propagation like we have the so-called deconv lab, like or like guided back pop or whatever like that couple approaches. And we also mentioned that okay, this is a visualization trying to understand like what each coefficient correspond to um, in the image, like what actually the lateral is doing. So this is important, right? Because if you think of the lateral, you want to know what exactly the lateral is doing. Um, Especially for some application, uh, for example, like for medical application, like if you say, okay, this thing diagnoses cancer, uh, you want to know like what the image. For example, like you just have an outcome, you have an image, you have an outcome saying, okay, cancer, not cancer. So now it predict it's cancer, then like maybe like in the middle of layer you have like something like you think it's like because of this guy is going to have like high score to believe it's cancer, then you want to know what this one is actually visualizing, right? So and to have the model to be interpretable sometimes very important. And another example, for example, like in robotic applications, um for or like any other application, there's a stake like kind of like uh, it's kind of expensive. For example, like if you have a robot, either it can like hurt someone or like autonomous driving, it can either badly injure someone or like that equipment is expensive to crash. So you want the model is kind of more interpretable. So then the visualization is a mean to achieve that, like for you to really pop into the model to see like what's going on. And And we also mentioned that some CNN application for us, that trying to visualize kind of like, for example, we have deep dream and also like change the style. I don't know like about like music, like whether anyone do anything about that. Like this is probably like an interesting direction, but yeah. Probably like someone did something already. Like for example, you have a song, then like you change the style somehow. Like
Yeah,
you find that.
I've seen that for music.
Yeah, that's very nice. Yeah,
It's interesting.
yeah. I don't know how good is that though.
It's not very good yet, but
Yeah,
they're working on it.
yeah, I know. I saw some random synthetic music like mm, it's okay. Yeah, but I don't know
Yeah.
how the style transfer though. Uh,
Well, they can do different genres and kind of fuse them together, so that's kind of
yeah.
neat. But the just like as far as like the quality of the sound goes, it's not very good. It's mostly just kind of like tones, like MIDI type
Okay.
tones.
Yeah, I'm very acceptable for music. Like I mean the sense I yeah.
Yeah.
Uh so um yeah, that's is actually a very interesting direction. I don't know. Right. So and this I okay, I finally to fully classify, but this is not just for new lecturers and also for CNN, but like for every lecturers as well, essentially. So okay, I guess I'm filming this early. So but I guess I don't have much stuff because I otherwise I need to start a new topic. So you guys have any? Oh, by the way, like don't forget to get your review peer review done. So it should be due like this weekend. And we have a hard deadline for this one. So so please I just finished that.
Do you mean the
Yeah, presentations. Yeah,
oh, the presentations?
yes.
Okay.
And also yeah. Remember that like next Tuesday, I believe is an instructional holiday, so there will be no class Tuesday.
I
So
think we also have project
yes, I think
not proposal, like a progress report due soon.
yes, I think so as well. And maybe I don't know whether homework already due. Oh yeah, no, or not. So yes. So okay, if there's no question, I will see you guys next Thursday then. Um
Thank you.
thank you.
Thank you so much, Professor.
Yes.